Assalamu alaikum and welcome to lecture number 3 on uh, operations on signals. So in the previous lecture we have studied about the uh, signal and its classification, right? So you understand that signal is defined as a function of one or more than one variable, and it conveys some information, right? So in this particular case, you all know that we'll be talking about we will be dealing with the one-dimensional signal only. So in this case, we are dealing with two variables. One is the independent variable and one is the dependent variable, right? So as far as independent variable is concerned, so in the first part we'll be talking about the independent variable will be the time. Okay, so we say this is time domain signal, right? Whereas in the second part where we will be dealing with the Fourier or Laplace, in that case the independent variable will be the frequency. So in the previous lecture we talked about the what is a signal and if it's different classification. So now we'll be talking about the operations on the signals, right? So you have the clear idea that because we are dealing with two variables, so one independent and one the dependent variable, right? So that means the operations can be performed on the dependent variable and they also can be performed on independent variables, right? So first let's look at what operations we can do on the dependent variable. So you understand we can do amplitude scaling, that is multiplication by a scalar, right? So in this case the amplitude or the values along the y-axis will be change. So similarly we can do addition or subtraction of signals, we can multiply the signals, we can differentiate or integrate the signals, and so on, right? As far as the operations on the independent variable is concerned, so you understand we have independent variable here t, r, and right, both are the time domain, right? So the operations that can be performed on the independent variable are the time shifting, time scaling, and time reversal, right? So let's first have a look at the operations performed on the dependent variable, right? So you understand dependent variable is basically x of t or x of n, right? So you understand based on the value of the independent variable we classify the signal into discrete time signal and continuous time signal, right? So the in case of continuous time signal, the amplitude scaling is defined as k times x of t, right? So where your input signal is x of t, you understand that's because t is there, so it will be a continuous time signal, right? So the corresponding output signal y of t, you understand that's a norm that we represent the input signal by x of t and the output signal by y of t. Similarly, input signal in case of discrete time signal, it will be x of n, and the corresponding out of signal will be denoted by y of n. So for example, we have signal x x of t the input and the output is y of t. So in case of amplitude scaling, we can write the equation as y of t equals to k times the x of t. Similarly, for discrete time case, we can say y of n equals to k times x of n, where k is the scaling factor. So depending upon the value of the k, we can have different signals. For example, shown here is the input signal. This is your input signal, right? And this is your output signal. So you understand if k has value greater than 1, in that case the output signal will be the amplified version of the input signal as shown here, right? So here, because k is greater than 1, so that means the output signal y of t, which is equal to k times x of t, is the amplified version of the original signal x of t, right? Similarly, if k is greater than 0 and less than 1, what does it mean? It means that k has positive value but it is less than 1. So when k is less than 1, that means the resulting signal will be the diminished version of the original signal, right? So that means you are reducing in terms of amplitude, and you understand we are doing nothing towards the time side, right? So it's not stretched version or it's not compressed version in terms of time. It is the replica, right? So it's exactly what you had at the input. You have exactly the same signal, but in terms of amplitude it is modified, right? So modification is based on the value of k. If k is greater than 1, the modification will be that you are actually amplifying a signal. So you can say that if your system is amplifier, right? So in that case, the output signal will be the amplified version of the input signal. So when this happens when k is greater than 1. But when k is less than 1 and greater than 0, meaning k is positive, so in that case you get the diminished version of the input signal. Similarly, when k is less than -1 and k is greater than -1 and less than 0, in that case again you get the diminished version of the original signal, but this time the amplitude inversion is also accompanied, right? So for example, we have k equals to -0.5. So minus indicates that the amplitude will be inverted. So you see, in the original case we have positive amplitude, whereas in the resulting signal the amplitude becomes negative. Why? Because k is negative. So when k is negative, it will be inverted. And also because k has values less than -1, so that means it will not be the amplified version of the input signal. It will be actually the diminished version of the input signal, right? So similar arguments apply to the discrete time signal, that if you have a discrete time signal and you scale it by a factor of, for example, 2, then it will be amplified version of the input signal. If, for example, k equals to -2, in that case the output signal is amplified but inverted version of the input signal, right? So this is how the amplitude scaling affects or changes the signal. The second operation can be addition. So this can be written as x1 of t plus x2 of t, or in case of discrete time signal, so here point by point addition, right? So for example, x1 of t has different values, x2 of t has some different values. So addition means you point by point add those values, right? Or if there is subtraction involved, so you just point by point subtraction, right? So you understand that x1 of t, which we also say that it's the dependent variable, it has different values, right, for a different point of time. So all the corresponding values, if you are adding the two, you will add, or if you are subtracting the two, then you will subtract the corresponding values of x1 of t, x2 of t from x1 of t as shown here, right? So the third operation that can be performed is the multiplication. So again, it's a point by point multiplication of the corresponding values of x1 of t and x2 of t. Or if this is a discrete time signal, in that case you multiply the corresponding values of x1 of n with x2 of n. The physical example of the multiplication of two continuous time signal will be the AM radio signal, in which we have x1 of t, that is your audio signal, right, plus the DC component of audio, right, and then the second signal x2 of t will be a carrier signal, right? So this is the example of how the multiplication is applied in practical systems, so that is your AM, or amplitude modulated, or amplitude modulation system, radio system, right? Okay, so another operation can be like, yeah, on the previous slide, it can be integration, or it can be differentiation, and so on, right? So there are so many operations, so these are just few examples. Now, as an example, we can say that the in electrical systems we have inductor, capacitor, resistor, and so on. And I hope you have idea that we can say anything that performs any operation on signal is termed as the system. So we can say that basically inductor, resistor, capacitor, amplifier, these all are systems, right? So we can say that inductor is system, and this is the equation for the inductor, right? So the voltage across the inductor is basically equals to inductance, that is L, times the rate of change of the current appearing at the inductor, right? So inductor basically performs the differentiation, right? So similarly, capacitor can be said as an example of the system where it performs the integration. So again, the input signal in case of capacitor is also current. So this is the input output relationship, and this is how the system, which is capacitor, is performing integration operation on the input signal, which is current, right? So integrating this, I think there is scaling fact I think there's a scaling factor I forgot to mention here, that is 1 by C. So basically we can write here 1 by C, which is the capacitance of the capacitor. So this is the exact equation for the this inductor capacitor system. So the voltage across the capacitor is basically equals to 1 by C times the integration of input current, which is ICT, and it's the limits are from minus infinity up to t. So shown on the right is the example of the two signal for addition. So we have a signal x1 of t that is defined from minus 3 up to 3. It is 0 beyond plus 3, and it's also 0 beyond minus 3. Then again we have another signal that is x2 of t, and it is defined from minus 10 up to 10. So it has value of 2, whereas the first signal has value of 1, and the signal is has value of 2 from minus 10 up to 10, and from 10 onward up to positive infinity, or minus 10 up to negative infinity, this signal is 0, right? So addition of this will result into this signal. So you can say that you can observe, right? So addition is just it is shown here so that you can understand how the variable addition is performed, right? So you understand from minus 10 up to infinity, this signal is 0. Similarly, from minus 10 up to infinity, this signal is also 0. So adding from minus infinity up to minus 10, this will result into 0 because both the signals are 0. So we have 0 here, right? Again, from minus 10 up to minus 3, this signal is 0. Whereas from minus 10 up to minus 3, this signal is 2. So that means 2 plus 0 will be equal to 2. So that means from minus 10 up to minus 3, the resulting signal will be 2. Again, from minus 3 up to 3, this signal is 1. Whereas from minus 3 up to plus 3, this signal is plus 2. So 2 plus 1, that is 3. So that means from minus 3 up to 3, this signal will have value of 3. Again, from minus 3 up to plus 10, this signal is 0. whereas from minus 3 up to plus 10 this signal is 0, whereas plus 3 up to 10 this signal is 2. So that means 2 plus 0 will result into 2, right? So that's why from a minus 3, right, from minus 3 up to 10 it will have value of 2, and beyond 10, right, this signal is 0 and this signal is also 0, so that means summation of 0 with 0 will result into 0. So that means from 10 up to positive infinity this signal will be 0. So this is how we add the two signals, right? So I hope that gives you some understanding, because you are very well familiar with the addition of the constants, but here you are dealing with the variables, right? So again, because we are doing a one-dimensional signal, so that means we have two variable here, that is, one is independent variable and one is the dependent variable, right? And again, this is the independent variable is t, so we call it time domain signal. So this is a time domain signal, and the value of the signal varies with time. So if you look at the first signal is 0, right, from minus infinity up to minus 3, and from minus 3 up to plus 3 the signal is 1, and again it is, right? So I hope this is clear to you that we do the addition point by point, right? So when we add two signals, similar is the case for the multiplication when we multiply two signals. So like here we did the point by point addition, there we will do the point by point multiplication. An example for that is the simple example, that is the AM radio system, in which we have two signals, that is your audio signal that you want to transmit, and the carrier signal. So we multiply point by point the two signals, right? So that's all about the operations on the dependent variable. Now we start the second topic, which is the operations performed on the independent variable. So you understand we are dealing with the time domain signal, so we have the independent variable time, right? So also in case of time domain signal, we have two versions of the time domain signal, because if the independent variable, which is time, if it is continuous, then we call it a continuous time signal, and if it is a discrete, then we call it a discrete time signal. In case of discrete time signal, the independent variable is denoted by n, right? So for example, x of n, that means x is n is the independent variable, and similarly if the independent variable is continuous in time, then we say the continuous time signal. So let's start with the first operation that we perform on the independent variable. So the first operation is the shifting, right? So you understand we signal shift to the right or to the left, right? So for example, we have input signal x of t, right? And from t you can tell easily that this is a continuous time signal, right? So the time shifted version of x of t is defined as y of t. Y of t is your output signal, which is obtained by shifting the input signal, which is x of t, by amount of t naught, right? So t naught here represents the shift. Okay, now we can say you understand that shift can be towards the right, that you shift the signal right side, or shift can be towards the left, where you shift the signal left side. So that depends on the value of t naught. So if t naught is greater than 0, what does it mean? It means if t naught is positive, right? So in that case the resulting signal, which is y of t, will be shifted right, and we call that y of t is the delayed version of x of t. So similarly, we can also say the same thing for the discrete time case, that the input signal is, for example, x of n, and the output signal is y of n, which is obtained by shifting the signal x of n by amount of n naught. So remember that in case of continuous time signal, t naught can have any value, right? I mean, it's a real values. Real value means it can have 0.1, 0.2, minus 0.1, plus 0.1, and so on. But in case of the discrete time signal, you understand discrete time signal is defined only at discrete intervals of time. So n naught should be an integer, not should be, in fact must be an integer, right? It cannot have real values. So again, similar to the continuous time case, if n naught is greater than 0, right? So we say yn is basically delayed version of the x of n. And if n naught is negative, that is if it is less than 0, then we say yn is basically advanced version of the x of n, right? So again, the same is the case for the continuous time signal. So if t naught is less than 0, that means if t naught is negative, then we say the y of t is advanced version of x of t, right? So we can also say it's basically shifted left, right? So here is example shown in figure A, right? So that's your original signal x of t. So if I shift it by an amount of t, right? Capital T is basically positive value, right? So if I shift it by amount of positive t, capital T, then the signal is shifted this side, right? So because you can also say that 0 means you are present, negative means the past, and positive means the future. So if you are pushing something towards future, you say you are actually delaying it, right? For example, you're supposed to do your homework now, and instead of doing it now, you say, okay, you will do it tomorrow. So right on the time axis, you understand 0 is your present, negative side is your past, and positive side is your future. So if you are shifting something towards the future, we normally say you are delaying it, right? Because it is supposed to be done now, but you are delaying it maybe for an hour and whatever amount of time, then we say it is basically delayed, right? So similarly, for example, you are supposed to do your homework now, right? But you have already done it. Then you say that you have, in terms of signals, you say you have shifted the signal to the left, or you say you have advanced it, right? So I hope you understand the terminology for the delay and advance, right? Similarly, in terms of payments, you say, okay, you have done the payment in advance, right? So I hope that's clear to you that what do you mean by future, present, and past. And if you do something, you're supposed to do it now and you're shifting it to the future, you say you're delaying it. Or if you are supposed to do something tomorrow and you do it now, so you call it, you have done it in advance. So you understand, in real life there are some things which can be done now. I mean, you can do it in advance, but there are many things that you cannot do it in advance. You do it on the proper time, right? So that means if you shift it to the right, you say you're delaying it, or you can also say, right? And if you're shifting it to the left side, so you can also say that you are doing it in advance. So here is an example of a signal xn that is defined for xn equals to 1, for n equals to 1 and 2, and xn equals to -1 for n equals to -1 and -2, and it is 0 when n equals to 0, right? And when absolute of n is greater than 2. What does that mean? That means for the values, for these values, this signal has this value, right? That is 1 and -1, right? So what does it mean? This means that absolute of n means negative and positive values of n, right? So for example, -3. So for -3, it will be 0. Minus 4, it will be 0. Minus 5, it will be 0. Again, for plus 3, plus 4, plus 5, it is 0. So that means you can write it like this also, that absolute of n greater than 2. So either positive n or negative n greater than 2, the signal is 0, right? So if we plot this signal, so it will be something like this, right? This is your n, okay, or maybe I write here, this is the n axis. Okay, so at -1, this is -1, right? So for example, this is -1, right? N equals to -1, and the value of the function is also -1, right? So it has a -1 amplitude or value. Then again at -2, it is how much? Again, this is the point where the index is -2 and the signal has value of -1. So for example, this is 0. At 0, it has value of 0, right? Then again, it says at 1 and 2, it has value of 1. So this is 1 and this is 2. Okay, so again at this point, it has value of 1. Again, this is 1, this is your 1, and this is the index is 2, right? And beyond this, it says absolute of n greater than 2. So whether minus n or plus n, so these, you see, this shows that they have 0 value. So this is your signal, right? So you see that at -2, it has value -1. At -1, it has value 1. At 0, it has value 0. At 1, it has value 1. At 2, it has value 1. At 3, it has value 0. At 4, it has value 0, and so on. So it has 0 values from -2 to plus infinity, and +2, I mean greater than +2 up to infinity. So it has only these 4 non-zero samples, right? So find the time shifted signal y of n such that y of n equals to x of n plus 3. So if you look at this one, what is the value of n naught here? So if you compare it with the standard equation, that means if you get plus here, it should actually be something like this, x of, right, at this x of n plus, you get +3, so that means this is basically x of minus 3, right? And why this is so? This is so because in formula we have x of n minus n naught. Now x of n minus n naught result into x of n plus 3, so that means basically n naught is -3 here. N naught is how much? It is -3. So when n naught is -3, that means you see this is the case. So when n naught is -3, that means the shifted signal will be the advanced version of x of n, or you can also say it will be the shift left version of the x of n. So how much shift left? Because it is -3, so the -3 means the resulting signal will be shifted 3 units towards the left. So that means the y of n, x of n is this one, so shifting this by 3 units, it will be, now it's -2, so shifting it by 3 unit, it will result into -5. So this signal will have values minus, right? Y of n will have value of okay, let me plot in fact. So I hope that is clear to you. So this is the n, and this is, for example, the 0 axis, right? This is 0. So this is your y of n. Okay, so if I shift this signal 3 units to the left, that means this point will be at minus, you understand, right? This is minus 3 unit means minus 5, minus 1 3 unit will be minus 4. Okay, so this point is 0, so this is now at what point? This is minus 3, right? Minus 3 is 0, then 1, it will be on minus 2, so this is minus this is right, so this point is minus 2, and minus 2 minus minus 3 is minus 1, so again we have another sample here that is at minus 1 location, right? And then this signal 3 minus 3 0, so at 0 we have 0, right? And so this is the resulting signal, right? So I hope you understand. Maybe you can discuss this in the class if it's not clear to you, but I have tried here to write it. So this is the example of a discrete time signal, and we have shifted it by 3 units to the left. And how do you know 3 units? Because it says x of n equals to y of n equals to x of n plus 3. So because in the original equation, if you compare this with this one, then that means n naught is minus 3, right? And how it's minus 3? Because it's plus 3 here, so we have a minus in the formula. So if I replace this with minus, then I have to write minus 3 with this one, right? So this is the shifted version of the okay, x of n, but how many units? 3 units, and also these 3 units are to the left because n naught, if I compare with the standard equation, I get minus 3. So if n naught is less than 0, that means we are shifting it to the left. Okay, so we can say that y of n is advanced version of the x of n. Okay, so this is how you do it. I hope this gives you understanding. So another operation that we perform on the independent variable is the time scaling. Okay, so again, we have input signal, continuous time signal x of t, and we scale it by factor of a. So we get output signal y of t, which is equal to x of a into t, right? So if a has value, positive value, right? It says that a is greater than 0 means positive, and a is less than 1 means it's positive value but less than 1. Okay, so in that case we say y of t is the stretched version of x of t, right? So the signal will be stretched. For example, we have so value of a less than 1 and greater than 0 means positive, and for example we have 1 by 2, a equals to 1 by 2, or we can say a equals to 0.5. So if a equals to 0.5 means y of t equals to x of t by 2, right? So if y of t equals to x of t by 2, then we say y of t will be stretched or version of the input signal. And if a is greater than 0, then we say it is compressed version of the signal x of t, right? So similar arguments apply to the discrete time signal, but remember, in case of discrete time signal, k can have a value greater than 1, right? Because if k is less than 1 means we cannot stretch the discrete time signal. We can use interpolation, but we just say that it's because in case of interpolation you are adding the extra information that's not exact values, right? So we can say that in case of discrete time signal we can have k greater than 1. So when k is greater than 1, we say that we get the compressed version of the input signal, right? So for example, so here's example of a discrete time signal for the time scaling, right? So because as it is given y of n equals to x of 2n, that means because k is greater than, you see, 1, so that means the scaling factor is greater than 1, so that means the resulting signal will be compressed form of the original signal, right? Because the scaling factor is 2, so that means the resulting signal, which is y of n, will be the 2 times compressed version of the original signal. Now if we look at this one, the original signal has non-zero values from n equals to -6 up to n equals to +6. So if we compress it by a factor of 2, right, I can write that it is -6 to +6, and if I scale it by a factor of 2, that means the resulting signal will have values that are dividing 6 by 2 will result into -3 to +3. Okay, so that means for let's just take the value of y of for example -4, right? Because we already know that the original signal is from -6 to +6, and scaling it by a factor of 2 will result into -3 into +3. So that's why I just take a value of -4 so that you have better understanding. So y of -4, replacing n by -4, that will -2 into -4 will result into -8, right? So you know, because it has non-zero values from -6, and at -7, -8, -9, it is 0, so that means it will be 0. So y of 4 will be 0. Again, y of -3 will be equal to x of, right? So -3 into 2, -6. So y of -3 will be equal to x of -6. So it has this value, right? So we get this value. Then again, because the next value will be y of for n equals to -2. In that case, n equals to -2 will be equal to x of -2 into 2x of -4. So we get this value, right? Again, using similar argument, we can say that we get -2. Again, we get this value, we'll get this value. These values at the even indexes will be skipped because we are scaling it by a factor of 2. So that means the resulting signal will contain the alternate signal. So we get this thing. So I hope this gives you understanding of what happens when we scale the discrete time signal by a factor of 2, right? So this is the resulting signal, right? And quite obvious that because the original signal is from -6 to +6, so scaling it by a factor of 2 will result into dividing this by 2. That means the resulting signal will be from -3 to +3. So let's take another example of the continuous time signal, right? So I hope just by looking at it you can tell that for a signal x of 2t, this signal will be compressed, right, by a factor of 2. So that means now it is from -1 up to 1. The x of 2t will be from -1 by 2 up to 1 by 2. And similarly, if I scale it by a factor of 1 by 2, that means the resulting signal will consist of like this now -1. So if I scale it by a factor of 1 by 2, it will be -2 up to 2. Okay, so I want you to learn how we can do it mathematically, because this is the graphical way. Okay, graphically you understand, because it is from -1 to 0 and 0 to 1. So I hope that's clear, right? Now let's see how we can define this signal mathematically and do or demonstrate this thing using mathematics. So I hope you have the idea of piecewise defined function. So if you look at this one, this is basically piecewise defined function. From -1 up to 0 it has one definition, and from 0 up to 1 it has another definition. So the overall function is the sum of these sub functions. So let's write it. Okay, so what will be the equation? So because this is linear, right, so we can find the linear function. So using linear geometry we can define the mathematical description for this signal, right? So you know y equals to, using basic geometry you have idea for a line equation, this is equal to mx plus c, right? You understand m is the slope, c is the y-intercept, and y is your function f of x, and x is your independent variable. If I translate it to the in terms of signal, so we can say basically x of t is y, okay, and in signal, in this particular part we are doing time domain signal, so time is your independent variable. So m is again the same thing, that is we call it a slope. So x is your time, because in geometry x and y, you understand, I think you can translate it. Okay, so the x was your independent variable. In this particular case t is the independent variable, so we can write it like this. Okay, now to find m, you know how to find m. We say m equals to y2 minus y1 divided by x2 minus x1. Okay, so this is your in mathematics you have, or you're in geometry course, you have done this, right? So if I translate it to a signal, so in signals instead of y2 and y1 we have x2 and x1, right? So we can say m equals to x t2 minus x, right, x t1 and divided by, and it will be t2 minus t1, right? So if you look at this part, that is -1 to 0, right? So for example, this is your xt2, so this will be xt1. So here we call this value t1 and we call this value t2. Okay, so that means m equals to at this point it has value 1, so 1 minus, at this point it has value of 0, okay, and again divided by, at this point value of t is, we call it t2, so it's 0, and this is t1, so this is -1, so 0 minus 1, so this will result into 1 minus 0 is 1, and 0 minus minus 1 is 1, so this is 1 by 1, which means this is 1. So that means this has slope of 1. So also to find the y-intercept, you find the value of x of t, where for the k when t equals to 0, so at this point t is 0, so value of x of t is 1, so that means c is equals to 1. C is also equal to 1. So by putting value in this equation, we find that this is basically, so we can say x of t, right, this is equal to, so if you replace value here, so m is 1, t is t, and c is also 1, so we can say x of t equals to 1 plus t, right? And what is the range of t? So value of t are minus 1 to 0, so we say minus 1 t and less than or equal to 0. Okay, so this is your one. Again, for this second part I will not do, you can do the things in a similar way, and you will find that basically the second part equals to 1 minus t, 1 minus t, and this is 0, 1, so this is how you mathematically define this waveform, this one, right? So now if I want to scale it, for example, by a factor of 2, so to find x of 2t, it will be something like x of 2t is very simple. You just replace wherever is t by 2t, right? So I can say that's 1 plus 2t, right? And the range will be, because if I replace t with 2, it will be 2t, it will be 2t. So to make it t, I will divide both sides by minus 1 by 2 by 2. So I get okay, I do for the one part, for the second you can do by yourself. Okay, so this will be, okay, this is minus 1 and this is equal to or greater than, okay, because we have t here, so I will replace by 2t and I get this thing. Okay, similarly for the this one, it will be 1 minus 2t again, so this will be 0 is less than or equal to 2t, okay, and this is less than or equal to 1. Okay, so that means if I simplify it, so t will be somewhere minus 1 by 2, okay, 2, 0, right? Similarly, this one can also be written like this, so this limit can also be written like this. So 2, if you divide 0 by 2, you get 0 t, right? So this is the range of values for which this signal is defined. So this will be 1 by 2, right? So I think now it's very easy to comprehend that if I replace t by 2t, right? So you see that the signal is stretched. Originally signal was from -1 to 0. So when I replace it by when I scale it by a factor of 2, so now the range becomes -1 by 2 up to 0. Again, for the second part, it was from 0 to 1. Now it is 0 to 1 by 2. So that means scaling a signal by 2 will result into compressing the signal by 1 by 2, right? Similarly, you can do by yourself for the second case, in which we scale it by a factor of 1 by 2. So if I scale it by a factor of 1 by 2, you understand this range, this will be expanded, and we'll have from originally it's -1 to 0. So if I scale it by a factor of 1 by 2, it will be -2 to 0, and this will be 0 to 2. So scaling by a factor of 2 will compress it, whereas scaling by a factor of 1 by 2 will expand it, right? So for the both cases, I have plotted the resulting signal here, and I want you to do the second part by yourself. Write the mathematical expression for the original signal, and what you can do is just replace t with 1 by 2 t, right? So in that case, when you do, I hope this will give you idea how we can, or actually how, when we scale a signal, what happens, how it compresses and how it stretches, right? So if the scaling factor is greater than 1, in that case signal will be compressed, and if the scaling factor is less than 1, in that case it will be stretch. So I think that's all for today, and we'll start the third signal operation, which is time reflection, in the next lecture. So go through the slides, and if you have any question or any problem, right, so we will discuss that in the live session. Until then, goodbye.